First of all, we'll play around with conductors. Normally we can solder solid strands. Sometimes we do that if you want to verify you have a good connection. What's nice about solid strand is that normally we can terminate it and splice it. We just twisting them together and stuff like that, right? Understand? We have a problem with that with stranded in that it wants to spread out. We call it bird cage and all the time. So what we do, and even over there, y'all can see, if you look at the Festo line, they have these pin connectors on the end that inserts it into the terminal board. Over here on the Amatro line, they decided not to do that. So when you take those things out, you probably notice they're all spread out. Now we don't have any problem over there because they're in a compression type terminal, which comes in and has a gap, and then when you screw the line down, it closes the gap, so the strands has nowhere to go, right? So all the strands still stay in there. But on other methods, what we do is we either terminate these with solder, or we terminate them with some type of crimp connector. Of course, the best would be solder, right? You understand that? So first of all, we need to learn how to strip them. So you need to, when you look at your stripper, you can see it's got gauges on the side. So after a while, you learn the gauges. This is about a 20. This is a 22 gauge wire. And what you don't want to do is you don't want to come up here and do this. You see a lot of people doing that. The problem is if you do that, if that blade hits one of these little things right here, little strands, then what it does, it scribes it, and then it will break off really. And so stripping wire is going to take a little force. So what we would do is we'd come in and we'd put it in, and then put it in the right gauge, and then just pull straight out. And it's not easy because what you're doing is you're basically scribing the insulator and then tearing it off, right? Y'all understand that? Then what we do is we have our hands washed, and then we'll come up here and we'll deliberately put this into a spiral. Most of the stranded wire that we deal with is just what they call a straight wire thing. So they just put them in there together, right? Understand that? When you get into the bigger cables, they'll actually start twisting them for you. Okay. Now, what's the advantage of stranded over solid? Yeah, so it's a lot more flexible, right? You understand that? So it's a lot more flexible. So it's easier to move this stuff around. And plus, it's a little forgiving. If we come up here and scribe this and we lose a strand, then odds are that'll be okay. If you scribe solid strand, it might work for a while, but eventually it's going to break, right? Y'all think glass, we call them glass cutters, but they're not glass. There's no such thing as a glass cutter. It's a scribe is what we do. We have a diamond blade, and we come down here and we scribe it, and now what does it do? It breaks real easy, right? And that's the same thing with metal conductors also. So what we're going to do, first thing you'll need to learn how to do is we call it tening. Now, tening is a process of coating something with solder, right? You understand that? We tin our iron, which we showed y'all. Okay. So we come over here, we pick it up, and the first thing we do is what? Clean it off, and you can see if you got a good tin iron, see how pretty that is? Not as pretty as my wife. And then what we do is we come over here and we'll try to do what we call a tin. I might have to go get a third hand for this to show y'all. What we do when we tin is we come up here and put I don't know if I got any tape up here. But what we're going to do is we're going to re-tin our iron, and then we're going to take it, and we're going to put it under the wire. Now you might have to touch it. You might have to touch the iron just a little bit, and then we're just going to pull it straight out like that. You see how fast that is? And what we've done is if you do this right, and I'll pass this around, you can still see the strands of wire, because what we're trying to do is we're trying to see the wetting. Does that make sense? So a lot of times we have to terminate wire directly into a printed circuit board. So here's a printed circuit board, which is what we're going to work with. And this is what we call a single-sided board. It's got both sides I think I showed y'all this the other day, right? Where we have these conductors that run across the surface. These are called traces. Some people call it foil. And literally, what they do is they start off with this whole thing coated with copper, and then we have a photo etch that we have available to us, and then you expose a mask to the light, and then whatever's exposed will wash off, and then we'll run it through an etchant material that'll actually etch off everything that's been exposed to light. And this has traces on both sides. You'll see that. And what we do is they go ahead and pre-drill these, and there's literally an eye that runs from this side of the board over to this side of the board. So this is the component side of the board, and this is the solder side of the board. Everybody understand that? Everybody okay? So what we would do is we would go ahead and take our wire, and we'd strip it with the correct gauge. And then what would we do? We'll twist it. And then what will we do? We'll tin it. Well, while I'm showing the way. So odds are you might have to mail order these. I don't know if Forbes carries these or not. Forbes Distributors, which is up on 4th Avenue. They sell a lot of electronic supply. Used to we had several plus Radio Shack, but Radio Shack basically went out of business. Around here anyway. I think there's still some around. So this is called a third hand. I've taken needle nose pliers before and put rubber bands around them just to make a big wide hole, like that. And you don't want to put the insulator too close, because what will happen is that when your insulation heats up, it'll get soft, and then your alligator clips will actually dig into it. So what we'll do is we'll come up here and tin the wire. By my solder. We'll tin the wire, right? I can see right off the bat. I hit that with my. So this is what we are to do to the Amatro line, is we're to take every one of those wires out and just tin them. Okay, now see how we do that? You can if it don't start flowing. Now the odds are most of the time it will. So what happens is sometimes we'll put it on there and I'll touch the top and it won't flow. It won't flow. Well, what I do then is I'll just put a little more solder and then I'll do it that way. I've seen people try to do this, and that's not the right way to do, because what you're trying to guarantee is you're trying to guarantee that the wire is melting the solder. And what's the soldering iron doing for it? It's heating it up, right? You understand that? So the function of the soldering iron is to provide the heat. And then we're supposed to get the metals that we're soldering together hot enough to actually melt the solder. Well, sometimes we'll tin it and we'll put it down there and it don't start flowing instantly. Well, what you'll do is you'll touch the tip of the iron right where it merges. And as soon as you see it flow, then you'll move to the other side. You always end up soldering on the opposite side of where you apply the solder. And we know that we don't do this garbage. We know, and you still see people do this. They solder like this. They'll put a ton of solder on that, and then they'll come up here and try to solder like that. Well, what happens? Well, what happens is your flux boils off instantly, right? You understand? And now, if you got any oxide at all, what's it going to do? It's just going to burn everything up, right? You understand that? Okay, so right now I'm on the bottom. So what's the opposite side of the bottom? The top. Okay, so you see when I'm soldering on the top, right? You understand? And I'm moving my iron across the bottom, right? You understand that? So sometimes you have to do that. I like to do it bottom to top. But what you don't want to ever do is you don't want to ever come in here and try to solder like this. Yeah, top to top. And I've seen videos on YouTube where that's the way they tin wire. But what happens is that if you try to put the solder on the iron and then transfer the solder to the wire, then what you'll end up with is you'll end up with what we call a cold solder. I don't know if I can demonstrate it with this or not. Well, what's going to happen is you lose your flux. So if there's any oxidation at all on that wire, okay, so I'm over here trying to do that, and it's just peeling off, right? You see that? Because why? My flux is gone. So you can, as soon as you see that puff of cloud right there, you'll see it. Now the flux is gone. Okay, y'all understand that? If we put it on there, and so, but we do tin this, you say, well, now the flux is gone, but why we tin the iron is to fill in that gap between the imperfections of the surface and the imperfection of the iron. So what it's doing is filling in that gap. The flux is there to remove the surface oxidation off of the devices that we're soldering together. So look, I'd sit over here all day long, and it's not taking solder at all, right? You understand? And if it does take solder, it's going to be cold, yeah, because it's not actually literally adhering to the surface. Yeah, that's a cold joint. So when we say the opposite side, it doesn't necessarily mean the top. It doesn't necessarily mean the bottom. It's wherever, whatever you can get to, right? You understand? But we always want to end up soldering where? On the opposite side of the iron. You keep your hands out of your mouth. Don't eat while you're doing this, right? Because why? This solder's got lead in it. Okay, pick it up, tin it, put it under the bottom, get up on the top, just slide it down. And you can literally still see the strands of the wire. Then what we do is, if we're going to solder this into here, is we're going to insert it from the component side, right? You understand that? Right? You'll see that? Now normally what I do is I'll bend it. And why do I bend it? Keep it from falling out, right? You'll see that. And then we'll come up here, and we don't, some people clip it now, but I don't. And then what will we do? We'll tin our iron, and then we'll touch it on one side, and we'll finish soldering the other. And then I didn't bring any little diagonal cutters. You can get a little pair of 6-inch diagonal cutters. They're really great. I'll go get some, and then we clip it off. What we want to do is we want to leave at least probably about a 1/16 of an inch above the solder, so we can still see it. Okay, y'all see that? Now, when we splice these things together, we've got several methods we can use to splice wire. And what we don't do, you'll see people do this, we don't do what we call a lap soldering iron. That's where you just lay the two wires on top of each other and solder them together. Because what you're doing now is your solder is not only providing your electrical continuity, it's also providing your mechanical support. What we want the solder to do is give us a good electrical connection, and we want the devices themselves, if possible, provide the mechanics, right? You understand that? Now, surface mount doesn't do that, but surface mount has got so many pins sticking out that, good gracious, you've got plenty of mechanical support, even though you're doing nothing but solder. So normally what we do is we'll come up here, and sometimes we pre-tin, sometimes we don't. Remember which. So what we're going to do is we're going to strip it. The first thing I'll show you is the weave. The weave is, I'll give you the smallest, the weave will give you the smallest profile. So what I'm going to do is I'm just going to feather these out. And then I'm going to come up here and feather these out. And then I'm going to put them together, usually 90 degrees apart. And then what do? Yeah, we just twist them together. And this is what we call the weave. And what's nice about the weave is that this gives you a real low profile, right? Understand that? And then, of course, we can come back and replace these. What we don't want to do is we can replace this with electrical tape, but most people that don't use electrical tape, we use something called heat shrink, and I'll go show y'all some of that. Heat shrink is a tube that shrinks down to about 1/3 of its size when you heat it up. So normally when we replace the insulation, what's the problem we have with tape? Is tape is being held on by glue, right? You understand? And glue normally over time does what? It dries out and stuff like that. So electrical tape, if you had electrical tape that's been on for years, odds are you can go and just move it back and forth because it's lost its grip. So this is called a weave. Now normally if you have a good solder joint, you'll see that the solder joint is usually stronger than the wire. So normally when you pull it and break it, it'll break right after your solder joint before it gets into the insulation, because that's the weakest point, is where it don't have an insulation. So the insulation is there to, of course, keep the push in, right, and it allows us to handle the conductors. If they didn't have any insulation on there, I could not handle conductors, right, while they were live. But also it does supply a little bit of mechanical support because it's wrapped around there. So normally when you pull these things, they'll break right where between the solder and the insulation is usually where they break. And normally they don't break at the solder joint. The other one, which people like to use, is called the rat tail. Rat tail, yeah. Because it looks like a tail when you get through. So the rat tail, what we do is we come up here, we strip our wire about 1/2 inch. Then we'll come up here and we just take them. I like to twist them together to keep them from bird caging so much, or spreading out. And then what you do is you take them, you put them at about a 30-degree angle. Y'all don't have to measure that, just put them in the X. And then we come up here and twist them together. And then what do we do? Now then we saw them. This is called the rat tail. Keep losing my solder, guys. Pick it up, clean the iron, tin it, come up here, touch it, then come up here, move it across. Now normally what we do here is we'll take it and we'll fold it over, right? You understand that? And either tape it or put a piece of heat shrink on it. But you can see the rat tail creates a pretty good profile, so the diameter of your splice will be bigger than the diameter of the wire. But this is a pretty strong joint too. This is a rat tail. The last one I'm going to show you is probably the strongest. This was developed when they were stringing, teletype wires all over the country. You used to use teletypes, right? Not teletypes, Morse code, the telegraph lines. And so this is what they came up then. So it's got the name Western Union. So what we do with the Western Union is we strip off probably about 1 inch. And we're going to twist them together. By the way, the bigger the gauge wire, you might have to do the strip in sections, right? You understand? So if you got a big gauge wire, if you're going to strip off a bunch of insulation, and you don't want to put a lot of stress on your wire, then you would do it in segments. Okay. So what we're going to do here is we're going to pre-tin each wire, because that's what you need to do. And I didn't bring any of those pliers, so I'll do these with my hand. And y'all get the idea. So I twisted them together. Then what I'm going to do, I'm going to pre-tin the wires. Oops. By the way, what's neat about solder, if you do get too much, your soldering iron are usually wick. So I got a little bubble down here at the bottom. I'm just going to come up here and keep cleaning off my iron, and then just keep letting it wick off. I might have to get solder. We do have something called solder wick, though, which is basically a lot like a wick on a candle, but it's made out of copper. And what it'll do is it'll wick that up too. And then we have a solder back too that I'll show y'all. That helps y'all take stuff out. What I'm gonna do is just. So what we do here is we're gonna come up here and we'll cross the wires up, right? Let's see what I'm doing. And then what I'm gonna do is I'm gonna come up here and I'm gonna take this one and I'm gonna wrap it around this guy. And this is the strongest one that we have. And then I'm going to take this guy, cut off too much. And then we're going to take this one and wrap it around this guy. And then normally you have some nail pliers so you can tie them down really good. So now what this is probably the strongest joint. It has a little bigger profile than the weave, but this is the strongest joint. So I can't. Normally what I would do is I would do some needle those pliers and wrap this around. Let's see if I can do that. I'm going to get up here in a minute. Like I said, I would normally just needle those pliers, but what I'm going to do is I'm going to go ahead and show you this. So this guy here, I can get it to lay over. Yeah, I'm trying to get it back flat. And I just don't have the right tools over here. I'm also go the other way with this guy. And then what we would do, we'd come up and do what? Yeah, we'll solder. And mine's sticking out a little bit over here, guys. But anyway, this is probably the strongest one there is. It's called the Western Union. What I said, I broke one of my rules. When you're dealing with integrated circuits and you lay them down, you don't want to ever put them like this with the pins up, right? You understand why? Yeah, people come up here and put their hands down on top of it. If you put it down here, you're going to crush the pins. And these are solid, by the way. You got to be real careful when you straighten them back up because solid wire, solid conductors, when you bend them a few times, they want to do break. So this is a printed circuit board, and this is a 16-pin, what we call it. We call this a DIP, or dual inline package. So what we mean is that there's two rows of pin, and they're in line with each other. So this is called a DIP. And what you'll notice, it's going to have a little notch on it, or it's going to have a little hole on it right here, a little dimple, I'm sorry, that indicates what we call pin 1. Pin 1, when you look at it at the top, it's the first pin on the left. And then what it does, it numbers down, so this will be pin A. And then you come across, and this would go up to 9 to 16. Okay? They usually don't tell you that, but somewhere on your circuit card, they're going to have silk screened on there how the orientation of this thing goes. So sometimes they'll put a what? A 1, right? because these guys are not Murphy proof. You can put them in backwards just as easy as you can put them in right. You understand that? So normally when you get these things and they're new, the pins will be spread out like that. So the first thing that we do before we try to put it in is we'll just come up here and up against a flat surface, and then we'll just push it down until we get it flat. And then we'll come up here, find the notch or find the little dimple right there, and line it up with pin 1. Right? You understand? And we'll see if it fits in there. Let's make sure. There it is. Now, once we get it in there, you don't want to force it. So, if you got any pins that are not exactly straight, you might have to come in and reorient. Pretty straight. Okay, now once you get it in there, what you do is you're going to turn it over and normally bend. I like to bend the pin, these two pins, catty corner of each other. Now, why? Keep it from falling out when you're trying to solve it, right? So now the thing's in there. And then what we'll do is, and also it adds more mechanical support, is we'll take these and then we'll come up here, take the iron, tin it, then we'll come down through here and just solder. I'm going to solder one away from it. And it don't take much solder, guys. And what's nice about solder is we can preheat. I mean, we can reheat it and let it melt again as much as we want to. So if I get too much solder, then we can use like a solder vac, or we can use a solder wick to get it off. I like the solder vac, and I'll get one of those to show you that. Now what you're doing is you're looking at the solder. So what you're doing is you're actually looking and watching the solder flow out. So and the more pendency people bubble it up, but if it bubbles up, so what we're looking for is we're looking for that volcano shape, right? That concave volcano shape. Now if we were doing a resistor, I'll do 2 of them. If I got some free resistors. And I didn't bring some needle nose pliers. What we want to do when we bend our resistor is you want to come up here and you want to lay it down. Right, you understand. And then you take your needle nose pliers and you see how much space you have. Everybody okay? And then you'll slide your needle nose pliers down there. And then what you want to do is you want to bend it. You want to bend it, put your needle nose pliers on this side, and you want to bend it on the opposite side. Everybody understand why? Because you don't want to put any stress wear in here. That might, this one's not angled, so it might not work out for this one. But it's going to be close. But needle nose pliers, they're angled toward the end, so you can actually check your gap. And then we'll insert it in there, right? It's not bad, pretty good. And then what we'll do, we'll come over here and bend it, right? I'll see that. Now some people clip right here, but I don't like to clip. I like to solder and then clip, but it's basically a preference. And then we're going to come up and do what? Pretend the iron, right? Come over and solder on the watt on the opposite side. Yeah. But if you don't see the solder flow, as soon as you put the iron down, when you touch on the opposite side, when you touch on the opposite side and you don't see it, the solder flow, move your iron over, touch it on the tip of the iron. As soon as you see it flow, move over to the other side. You understand that? Okay. And then we would take a pair of needle nose pliers and we'll come up here and we would cut these off. So this would be installed in an integrated circuit. We've installed a resistor. Didn't show you how to install a transistor. These, I can't remember what these cases are called. Some of your transistors will only go down to the depth they need to do. So if we looked at the integrated circuit, you'd probably notice there's a space right here. Because when you look at the IC, you'll see that it's got, starts off. So you want these things pushed in as far as they'll go. So this guy right here sets how high this guy needs to be off the surface of the printed circuit. Everybody understand that? Okay. So you push these things all the way down. Resistors that are under like a watt, you mount those flush. Your bigger resistors, you might want to leave a little space between the circuit board and the resistor because if it gets hot, right, understand that we don't want it to burn the board. Some transistors, so what they did here on these is they've got little spacers that come in that sets the depth of the transistor, how close it should get to the circuit board, right? Some of them can mount flush, some of them don't. The one we've used is a little TO92 case, and it literally will not let you go all the way down to the surface. We're not going to show you how to identify the pins on the thing. It's got 3 pins, by the way, and these all have tabs on them, which is pretty neat, which makes it real easy to line up if this information is on your circuit board. So notice on this circuit board what they've done is they put the tab so you'll line the tab up, and then it's got 3 leads coming off the bottom, and they're literally offset like this. If it don't have the tab, then you got to verify which direction it goes in there. And they're not Murphy, which means what? These guys, these type of case, they have a we call Murphy's Law. Y'all know what Murphy's Law is? Yeah, that's the short method that most people say. So these guys here, you would have to deliberately bend those pins out of order to make it not fit. So these guys are neat. So even if they don't put that information on here, they'll only fit in there one way unless you bend pins, right? You understand? The other ones that's probably most popular because they're made out of plastic. So these cost a little more money because they have a metal case on them. And usually they connect the collector to the case. So one of the leads are usually connected to the case because that's the lead that we call the collector. That's the lead that dissipates the most heat. The one we use, but a lot of your transistors now are going to be in plastic cases. And then they use what we call a TO92 case. And those suckers have got 3 pins coming out the bottom, and you could put them in there what? You could put them in there backwards. These, you would have to deliberately bend the base out to the other side to put this in. Right? You understand what I'm saying? But what you're doing is you're swapping the function that won't work. Yeah. Well, that's not exactly true. It all depends on what's going on. Transistors, we went over there and we looked at how much voltage that inductor puts out, right? Well, what we have is that if we put this thing in there backwards, we have a rating on your transistor called breakover voltages. And those don't even sound good, right? If you exceed the breakover voltage between any lead, then what happens is that you will damage the device. So the leads that we have, if we draw the symbol just for an NPN transistor, now this is the electronic symbol. Now this guy right here, we call this the collector. So the three leads on the transistor are called the base, collector, and emitter. And here's your valve right here. Your valve is between your base and the collector. Well, what happens is we come over here. The collector usually goes up to a big power supply. So this would up here would be 24 volts. And then what we would usually do with the emitter, if we're using this as a switch, is we would connect this to common, and then we open and control the valve with the base. Very small current. So this base right here, this junction right here is not designed to be reverse bias. This junction right here is always reverse bias. So the base to collector, we have no problem. It's designed to be reverse bias. So normally if they say this thing has 50 volts breakover voltage, collector to emitter, and then they'll put O. So if you ever look at V sub CEO, that's the breakover voltage between this. If you look at the base and the collector, it's going to be the same thing. So that means I could put 50 volts between a difference in potential in reverse bias between the collector and the base and not hurt this thing. You look at this base to emitter, it's going to be on the range of about 7 volts. So that means if I reverse bias this thing by 7 volts, then we got problems. Well, the problem is if I put that thing in there backwards, what I've just done is I've pointed this thing up here toward what? Plus 24. And my collector is coming down here and it's connected to common. So if I get over 7 volts between this lead and that lead right there, then you just blew your transistor. So yeah, you could definitely blow it. It depends on what type of protection, what size resistors you have in there that limit the current flow backwards to the emitter and base. So it could survive or it might not survive. So it's hard to say, Kurt, what's going to happen. There is that potential though, is you can bop it. And the same thing would be true with a PNP. If you reverse bias that emitter to base junction, and that's what would happen when you put it in there backwards, right? You understand, you reverse bias the base to emitter junction, and it's not really made to reverse bias it, because that would turn the transistor off. Can I ask you a question? If you put it in there right, you're not going to hurt it. If you put it in there backwards, it depends on what type of resistors you have available. So we deliberately in solid state, we have a little transistor, we have a little diode, and we deliberately reverse bias this thing. And it's got a breakover around 100 volts backwards. And then what we do though is we come up here and we put a 10 mega ohm resistor right there. So even though it breaks over, we don't let hardly any current flow through it in the backwards direction, so the diode survives. But what we're trying to do is trying to show those people how these things will do what? They'll break over if you exceed the breakover. This is voltage collector to emitter with the base open. So if I open the base, the transistor's cut off, period, right? Because the base is controlling the lead. So that would be like me going up to a water fountain and break off the control lead. So it's not going to do what? It's not going to cut off. So this is the amount of voltage. So this is not a light switch. This is a transistor. It's a semiconductor. There is always a path between the collector and the emitter. But it's designed to let current flow in one direction. If we force it to flow in the opposite direction, then the diode or the P-N junction is going to be screwed up. So what this means, this is voltage collector to emitter and the base is open. So if the base is open, then that means the transistor is definitely what? Off. And now the transistor is acting like an open switch. And if it's acting like an open switch, that means what? That means it's supposed to be off, but it's not a switch, it's a transistor. There's a path through there. And if I put enough difference in potential and I have a path, I will have current flow. But that current flow is going to be with a lot of voltage and it's going to burn that transistor up just like that. If you ever exceed the reverse breakover and don't protect it, So what we do in our lab is we'll come over here, and I think we have to get up around 90, around 100 and something volts up here, positive. And then we'll see this. So normally this guy right here is almost conducting no current at all. So we'll measure across that 10 mega ohm resistor, and it'll measure a little bit of current because there's no such thing as there's always current flow. And then you'll see it when it breaks over. So the voltage drop across your 10 mega ohm resistor will shoot up real fast. But what you did is you just broke the transistor off, but your current is almost nothing because we're protecting it with what? A 10 mega ohm resistor. Now, if I raise that to 500 volts, then odds are the 10 mega ohm resistor couldn't even protect it. So even all your semiconductor devices have what we call a breakover voltage. That means when you reverse bias them, when you put the wrong polarities on them, and you exceed a certain voltage, it will conduct all of a sudden. And then after that, it'll get hot, then it'll conduct more, it'll get hot, it'll conduct more, and it just avalanches after that. Now we do have a special diode that can handle a pretty good deal of reverse bias. It's called a Zener diode. It's designed to operate, but we will always operate this with a resistor in series with it. If you let it break over and you don't protect it, if you don't limit the reverse current, then what happens is you will go bad. Now, what's so neat is that when these guys here break over, if they didn't damage, they'll come over here and almost maintain a constant output. So Zener diodes are our voltage regulators. So if it had a breakover voltage at 5 volts, and I came up here and put 10 volts over here, then this guy over here would measure 5 volts. But we're protecting it with a what? With a resistor. So Zener diodes, those are our voltage regulators. So every voltage regulator that you have usually uses a Zener as a reference. So that's the symbol for a Zener diode. We have different types of diodes. But if you ever let this current get too high, so a Zener diode has a rating called PZ max. You know what that probably means? P usually use what? What do we use P to represent? Yeah, power. So when this thing here reverse biases, current flows through it, so it's going to start producing power. If you exceed the PZ rating of the Zener, it'll burn up. But as long as we operate it below PZ max, as long as we operate below that, then we can do that. So if you do take solid state, we'll teach you these things, and we'll show you how to calculate this resistor to keep it from burning up over whatever range your power supply operates at. So solid state devices don't like, if you turn them off, if you reverse bias them, then odds are most solid state devices, if you exceed that breakover voltage, they're going to be damaged. So that was a good question. So yeah, so if you put it in backwards, you could break it over, right? Are we okay? This is the TO92. TO stands for transistor outliner. So just follow your, now, the problem is we have tons of devices that use this 3-pin package. So just because you see this in a 3-pin package, don't think it's a transistor. We have SCRs that come in this package. We have triads that come in this package. We have voltage regulators that come in this package. We have temperature sensors that come in this package. So just because you see this package, it's an open source package. So that means anybody can do what? Anybody can use this case right here. So when we talk about a transistor outline, it doesn't define it as an element. It just means anything that needs 3 pins, 3 connections to the outside world can be in one of these. So voltage regulators, all we need is an input, we need an output, and we need a common. So that's 3 pins. So a lot of voltage regulator comes from this. So this is a TO92. This is a TO92, and these are 2 different things. So you just can't go out there and say, well, here's one, right, and pick it up. So you're going to have to verify the part number. So normally the part number's on. This is a 2N. This is a 2N. It starts off with 2N. There's a high probability that it's a transistor, because 2N indicates it's got two junctions, and that's what we got in there. This is a 3409, which is a PNP transistor. This is a 3904, 2N3904, which is an NPN transistor. Now the problem is there's no standard arrangement for transistors that use this pack. So this one, the emitter's on the left if you look at it from the front. So we think this is the front. It's got a flat side. Emitter's on the left, base and collector, which makes sense. But I've seen them where the collector's been in the middle, so there's no standard arrangement. It's up to the manufacturer. So what you need to do, if you need to replace one of these things, you need to look up the part number, right? You understand, and get that same part. Everybody understand that? But that's the problem we have with these, because I can put these in there backwards. I can put them in there frontwards. All right, you understand? If I put her in there backwards, it could be what? Damaged, right? Right, you understand that? And this might be the base on that side. This might be the collector and emitter, or it might be vice versa. There's no set arrangement on these things. And you see these a lot. These are cheap. I don't know how much we pay for them. We can look it up, but I think it's 20, 30 cents. If I went to a metal case, that's going to be already going to be a lot more money because of the metal case. So you're going to run into a lot of these plastic things like this. Yes. And the problem is, though, is that they're just basically written on here. And usually when the part goes bad and burns up, what usually happens? Yeah, it burns the number off. It's gone just like that. We've had this happen before, too, where we've had a resistor burn up and it burns the color code off of it. By the way, when you put your resistors in there, you want to make sure or try to center them up. So this one, he's got this off center, but if you look at the rest of them, they're centered up, right? You understand that? And normally this is what I'm talking about on the needle nose pliers. So they start off with a very small gap, and then they move up. So what you can do is you can center your resistor or your components and put your needle nose pliers and line up where the hole's at, right? And then do what? And bend it on the opposite side. Everybody understand that? And these are the diagonal cutters. We got some over there in the box I was talking about. These, if you're going to do printed circuit boards, these are the guys. You don't want to use a big old pair of needle nose pliers. Another thing, I started to cut this off, but I remembered I needed to show you that. When you cut these leads off, you need to put your finger on the lead before you cut it off. And why is that? Well, know what happens when that metal snaps? Usually that lead goes flying across the room. Anybody ever did that? Cut some solder strand wire and it goes like a projectile. But if you just take your finger and put it on there, then you're okay, right? And then we'll need to cut the wire. What you want to do is you want to try to cut it perpendicular. If you cut it at an angle, then you got a knife blade down there. You understand what I'm saying? So we want to try to cut it perpendicular. Oh, that's all. So what happens is people will cut it like this, and then you got a knife blade right there, right? Understand? And now when you handle that circuit board, it's going to cut you. And you see people do that all the time. If you can, what you want to do is cut it what? Yeah, straight across, right? You understand? If you can. Everybody okay, but you don't need to hold the board like this and then move it across you because you're going to scratch yourself up, because we call them pins for a reason, right? So those conductors that come out of these leads, we don't usually refer to, especially on printed circuit, IC integrated circuits. This is surface mount, by the way. The person that did this did a okay job. And while we're depending on this, you're depending on this to the solder is giving you all the support. So it's doing not only the electrical, it's also doing the mechanical. But these guys are usually real small and they have a lot of pins, right? You understand that? So they get their strength and they get their mechanical support with numbers, right? Any other thing, we're going to do what? We're going to give it a mechanical support by bending the pin. I think there's a lead I didn't solve. Are we okay? So are we ready to start soldering? Yes, no?
Yes.